Hi and welcome to this course on neural style transfer with TensorFlow. In this introductory chapter, we will take a look at what neural style transfer is and what are we going to do in this course. But before that, let me just make sure that we are familiar with the RHYME interface. So you can see a video recording on the right hand side of your screen. This is my screen recording of a virtual machine that I'm using on RHYME. And on the left hand side, you should see your own virtual machine. And I've already installed everything you'd need for this course on your virtual machine. So when it launches, you should see a Jupyter notebook loaded up. There's no code in this notebook, but as we go through the course, you should follow along me and type out the code in these blank cells. So just make sure that you have the NST Jupyter notebook loaded. All right, so back to neural style transfer. Before getting into the technicalities, let me just show you what it is. So if you want, you can actually go to this link and look at this image in your machine as well. This image is available on your machine as well. Right, so take a look at these three images. This is one, this is the second one, and this is the third one. The one on the left is our content image. The one in the middle is called our style image. And then we write an algorithm to generate a new image, the one on the right, where the algorithm basically tries to retain some features from the content image and apply the style from the style image. So we get our content image sort of stylized in the style of this style image while retaining some features of the content image. So it kind of looks like this cathedral, but also has some stylistic elements from this painting. So this technique was proposed by L.A. Getis, Alexander S. Ecker, and Matthias Petke, and I hope I pronounced these names correctly. They wrote a paper back in 2015 called A Neural Algorithm of Artistic Style. Right, so there you go. This is what we are going to do in this course. We will take this content image, we will take this style image, and then we'll write an algorithm to generate the content image in the style of the style image, which will look something like this. So let's get started. Welcome back. Let's start by importing a neural network model, which we will use to perform the neural style transfer. The way this algorithm works is by using a pre-trained model on a large image dataset. The intermediate layers of this pre-trained model work like feature detectors. We will use the output of these intermediate layers, or I should say intermediate feature detectors in this context, and compare that output for say our content image versus a proposed stylized image. This comparison can give us a content cost. Similarly, we can use the output of some of these intermediate layers with a style image and compare it with the output of these layers given a proposed stylized image. This can be our style cost. Then we add the content cost and the style cost together to get a total cost. Now, if we run an optimization algorithm to try and minimize this total cost and updating the proposed stylized image along the way, we should get a result which retains some features of the original content image but also imparts the stylistic features of the style image to the proposed stylized image. This proposed stylized image is also called a generated image. The original paper uses VGG19 model, and fortunately it's really easily accessible with TensorFlow, so we're going to use that. So let's start by importing TensorFlow. STF. I'm going to use the eager execution mode, so we will enable eager execution. And let's import the VGG19 model. So the Keras implementation in TensorFlow makes it really easy. Go to TensorFlow Python Keras applications.vgg19, and from this submodule you can import VGG19. In caps, this is the model that we're going to use. Right, so let's execute this. Press Shift Enter, or you can also press this Run button right here. When a code cell is under execution, you will see an asterisk pop up like this. And once the execution is complete, then this will change to a number, which will correspond to the sequence of execution for various code cells. Now, this might take a few seconds, so don't worry about it. As in, don't worry if it takes a few seconds. And once the execution is complete, then you can move on to the next code cell. And if the execution is not complete, you can pause the video. Right, so let me instantiate the model that we would have loaded and call it simply. Use the VGG19 model here, and we actually just need to provide a couple of parameters here. I'll set the include top to false, and I will set the weights to ImageNet. What is this? We are setting the weights to ImageNet because we want our model, which was pre-trained on the ImageNet dataset, so that it works like a feature detector for us. And the reason we are using we are setting include top to false is because we don't actually need to include the top layer, since we don't actually want the output of the entire model, but we just want some of the intermediate layers. So we don't need to actually include the top layer at all. Also, we will set the trainable parameter of the model to false. This is because we don't want this model to update its parameters as we uh, run our algorithm. We just want to use this for outputs, and that's it. All right, and if you want, you can take a look at the summary of the model. Let's run this code cell, shift enter. And this is a fairly large model. If I remember correctly, this is about 800 MB. So it might take a few seconds to load up. So don't worry if it takes some time. It's supposed to. And you can pause the video. If it's taking too long, then you can just pause the video and resume when the execution is complete of this particular cell. All right, so once this is executed, you will see our summary of the model. Now, this is a fairly big model. It has almost 20 million trainable parameters. In this case, we are of course not training the model, but it does have 20 million parameters. So that's quite a lot. And the way it's laid out is that it has 5 blocks. Each block has a few convolutional layers and followed by a pooling layer. All right, so if you want, you can look at this summary in more detail. So you can see we have block 1, 2, 3, 4, and 5. And for every block, you have some convolutional layers followed by a pooling layer and so on. All right, so great, we have the required model loaded up. Now let's go to the next chapter and load the other libraries that we will need, and along with some helper functions. Welcome back. The helper functions make it really simple for us to load and process our images. Now we'll define a function which does all the pre-processing for us using these helper functions that we imported in the last chapter. We want to transform an ordinary image into a format that the model can understand and work with in an efficient manner. And we will take the help of the preprocess input method we imported previously. Okay, so let's go to the section where it says image processing and display. And in the first code cell, let's define a new function. Let's call it load and process image, given some image path. Right? So image is going to be set to load image, the helper function, given the image path. Next, we are going to convert this to array. Image to array. Then we will pre-process this to make it suitable for the VDG19 input. And lastly, we are going to expand the dimensions of this array. Now, the reason we are doing this is because our model expects a 4-dimensional tensor. So what's going to happen is the first one that we are shoving in here is supposed to be the number of examples. And we have only one at a time. So we don't need to do anything else. We just need to expand this dimension. Okay. So now this 3-dimensional, right now it's an array, so it becomes a 4-dimensional one. And then we return this image. Okay, let's run this, shift enter. Awesome. Now let's write one more function that will sort of deprocess our images and display them in the notebook. We'll call it something like display image. Now you might say that why do we need to deprocess and then display the images? Because, why can't we do that before loading them and processing them? And the reason is that our intention is that we should be able to use it on a generated image, which would be a proposed stylized image. So that would be a processed image because it will be in the format of this pre-processing, because we would have processed our input content and style with the function above. Essentially, the results from the intermediate layers that we are going to get from those inputs are going to be arrays, and in order to display those as images, we will have to convert them, deprocess them in a way that becomes useful for our consumption to a human understandable image. Right. So in order to do that, we will do one function to do something opposite of this pre-process input, and another function to display the images. All right. So let's write preprocess given x, and in this case, x is just going to be an array. And what you want to do is set the channel information here differently for each channel. So for the for channel 0, or you could also call it 1, 2, 3. I'm just going to call it 0, 1, 2. So for channel 0, we're going to add it with this value. For the next one, we are going to add 116.779. And yes, you must be wondering, why are we adding these particular values? And the answer to that is simply we are doing opposite of what this preprocess input function does. And in our helper functions, there is no readily available function which does this, so we are writing it ourselves. Uh, we have a readily available function which does the pre-processing, but not the one which does deprocessing. So this is just reverse engineering, essentially. Right? Then we will set x to x and all the values, and inversion. So this is just to do the opposite of what the preprocess input does. And one of the things that it would do is invert the order of the channels. So that's basically what this line of code does. Okay, now we are going to clip our final values between 0 and 255 because that's what the pixel values are supposed to be. And also change the type to expected uint 8. And that should be it. We will now return this. And let me scroll down a little bit because we need to still write a method to display the images. So this only does deprocessing. It doesn't do any displaying. For that, we will write one more function. And this one will take a processed image. All right. Now, if the length of our image, if this is a 4-dimensional array, we need to do opposite of what we did before, the expansion of these dimensions. We need to actually squeeze that dimension out. Right? So we get it back as a 3-dimensional array that can be displayed as an image. Of course, we also need to deprocess. And this will just do call this function and return us the deprocessed values. And let's set the plot grid to false, the x-ticks to blank, the y-ticks to blank, and finally the image. Great. So let's execute this code cell. Now, just to make sure that you understand what's happening, we will call a display image method with the processed image. It could be our generated image. And then we will remove the axis where it corresponds to the number of examples. Then we deprocess it. And deprocessing simply means the opposite of this preprocess input function. So this is what it means. Different channels get added. We'll add different values to them. We sort of denormalize it here. Change the order of the channels as well. And then clip the values from 0 to 255, which is what is supposed to be in images. These would be your pixel values. And then we display the resulting deprocessed image. Okay, awesome. So now we want to make sure that this works. Let's test it out. And also to show you guys the style and the content image that we are using. You've already seen those in the first chapter, but let's display them here in the notebook. Okay, so let's display image and load and process image. The style image is simply called style.jpg. I think that's what it's called. Oh yeah, and here it is. This is the style image. And the content image is simply called content.jpg. So load and process image, content.jpg. There you go. And this is the Exeter Cathedral. And this is the Great Wave. This is a very famous painting by a Japanese artist. I don't remember the name now, but you can look it up. It's called the Great Wave. Okay, so brilliant. Let's move on to the next chapter and create our content and style models. In order for us to compute content cost, we need to take a look at the activations at some intermediate layer. In VGG19, there are 5 blocks as we discussed before. So these 5 blocks of layers with each block made up of 2 to 4 convolutional layers followed by 1 pooling layer. For content cost, we want to use activations from a layer by which layer the features, because these activations are essentially our feature detectors. So we want to use activations from a layer by which layer the features are already well represented, so that when we compare this output with the proposed stylized image, these features match in the 2 images as we try to minimize the overall cost using some sort of optimization algorithm. So more specifically, we are actually going to use block 5's second convolutional layer. So let's scroll down and find a section where it says content and style models. And you will see a blank cell below that. There we go. Click on the blank cell. So our content layer is going to be fairly deep in our model. So this is from the last block, so it's quite deep. So by this layer, the uh, complex features are already recognized, which makes sense because this whole cathedral is quite complex, so the overall thing should be reflected. Now, for the style cost, we can do something similar. In this case, we are going to use 3 different intermediate layers from 3 different blocks to compute our style cost. Now, we're using 3 different blocks in this case, and this is because we want different kind of stylistic features to impact our cost, and not just the high level or highly complex features extracted from the style image, but also from the earlier images, from the more shallow, from the earlier layers, and from the more shallow layers. So we will use these 3 convolutional layers from different blocks in the VGG19 model. Some will give us low-level, broader understanding of the stylistic features, and others will be more complex and uh, more comprehensive. So the style layers, let's use block 1. This will be pretty shallow, conv 1. Then we have block 3, conv 1. If you want, you can change these. I'm using only 3. In this case, the most examples will use 5 with the VGG19. And that's because in this particular example, this will give us a good result. I've already run this example before, so I know that. And also because this will, using less number of style layers will help us speed our computation. All right, so we know which intermediate layers we are using in order to extract features and then compare them in the original images and the proposed image. But how do we get the activation of intermediate layers? We know how to get the output of the entire network, but for getting the output of intermediate layers, we will have to create different models with those different intermediate layers as the outputs. So in order to create a content model, for example, we will do something like this. Let's say content model is going to be model. This is the model class we imported from Keras. And the inputs are going to be set to model.input. Very simple. So it will have the same input as the VGG19 model, but the output is going to be different. And output will be from the layer, you guessed it, from the content layer. Dot output. So we call the model VGG19 model and we get the layer which has the name block 5 conto in this case, and we access the output of that. And that creates our new model. So everything between this output and the input is exactly like our VGG19 model with the same weights as the VGG19 model. The only difference is that the output is different. You can imagine it that basically stops at this particular layer. Great. So this is it. And now you can probably imagine what we are going to do to create the style models. It's going to be exactly the same thing, but basically for 3 layers instead of 1. So we will have 3 models. So how do we do that? The easiest way would probably be something like this. Say style models and a list of models where the inputs, they're going to be same. So they're just the input for the VGG19 model. But the outputs are going to differ. So we will have outputs set to model.get layer, get layer, oops, model.get layer, and the name of uh, one of these layers, right? So we'll just iterate one by one. Let's just call it layer. Let's call it layer simply. And output. Model.getLayer.output, which is exactly like this one. But the difference here is that we will have to run a loop for layer in style layers. That will give us a list of the style models. Awesome. So we get a list of models for computing our style cost with each model using a different intermediate layer for the output. Great. So let's go to the next chapter and start computing these costs. But before that, of course, don't forget to run this code cell. All right, see you in the next chapter. Welcome back. So content cost is quite simple to calculate. We need to find out the output of the content model with both the content image and the proposed stylized image. Let's call this proposed image the generated image from now on. So go to the section where it says content cost and let's define a function called content cost. We'll take the content image and the generated image as input. And we will first have to calculate the activation for the content as well as generated images. The way to do that is just call the content model, pass the content image, and for the generated image, we'll do the same. Pass the generated image. now that we have the activations, we can simply calculate the mean squared difference between these two, and that will give us the cost. Reduce mean EF dot square A underscore C minus A underscore. Okay, so this gives us the so this is the difference between the activations, and then we square that. So that's the square difference, and then we calculate the mean. We'll return this cost. So we calculate the mean square difference between the activations that we get for the content layer. And that's pretty much it. As you can see, this content cost could be a good indicator of how close the content and the generated images extracted features are at the content layer. Great, so let's execute this, shift enter, and let's move on to the next chapter and define what is called a gram matrix. In order to compute the style cost, we will need to define what is known as gram matrix. We calculate gram matrices for the activations of the style and the generated image, and calculate the style cost by finding the mean squared difference between these two matrices. Gram matrices give us a strong feature correlation. And you could try using other techniques here, but the original paper on neural style transfer uses gram matrices, so that's what we are going to use here as well. But the fundamental idea is that we are going to use these matrices to match feature distribution as opposed to presence of specific features. Let's define gram matrix, and given a in this case it could be a tensor or a numpy array. Actually, it'll be an array. So let's find out the number of channels. Shape and the last one, so that will give us the channels. And let's reshape our matrix in a way where we convert, we basically have, instead of it being a 3-dimensional array, it will convert to a 2-dimensional one. So if we have a matrix of the shape 200 by 200 by 3, which would be typical for an image, we are reshaping it to be 200 multiplied by 200 by number of channels, which is 3. Okay, and then number of elements that we get after doing this type of reshaping. So that's df dot shape A, and the first element, that'll be 200 multiplied by 200. And then we calculate the gram matrix, which is simply matrix multiplication of A transpose A with A. So we do that. Transpose A is set to true. Okay, so this is just a matrix multiplication. And we also scale it down by 10, the number of elements. So that is how you define the gram matrix. Like I said, the idea here is to use this gram matrix to match feature distribution on two given images. So let's do that when we compute the style cost. We will actually compute the style cost with the help of these gram matrices. Okay, so let's do that in the next chapter. And before that, don't forget that you need to execute this code cell. So press shift enter, and great. I'll see you in the next chapter. We have a bunch of style models, each corresponding to a different intermediate layer from the VGG19 model. So our total style cost is going to be a weighted sum of the cost, weighted sum of costs of each of the models. So let's see how to do that. First, we need to calculate the weight. So this is simple to do. We'll just say 1 divided by the number of layers that we have, so or number of models that we have. Now this is assuming that the weight for each style model is going to be the same, but if you want, you can set them to be different, and if you want the stylistic features from one layer to be more prominent than any other layer, and so on. So you can make a list of different weight values in that case. Okay, let's define style cost given the style image, of course, and the generated image. So let's just say our J style is 0 at the start, and then we run a loop and iterate over all the models. And of course, I mean all the style models. So this is not actually that complicated because it's pretty similar to what we did for the content cost. We will first find out the activations. So activation for the style image, and of course for the generated image. Now we will calculate the gram matrix for the style image, the activation that we have got from the style image basically, and similarly for activations that we have for the generated image as well. Okay, looks okay so far. Let's calculate the current cost, which is the style cost in this particular iteration. And this will be the mean square difference between the two gram matrices, which are giving us the feature correlation. So we get TF dot reduce mean, TF dot square, GS minus GG. And of course, we need to add it to the overall cost. So J style plus equal to current cost multiplied by lambda. Okay, and that gives us the total style cost when this loop is run for the 3 times. In this case, it's going to run for 3 times. The style cost will, for the current style cost for each iteration will be added to the overall style cost. And then finally, we will return the style cost. Okay, so now we know how to compute the style cost given a style and a generated image. So let's execute this code cell. Great. Now it's time to run a training loop and try to minimize our total cost, which is going to be a weighted sum for our content cost plus the style cost. Welcome back. And now we are in our last steps. And in this chapter, we are going to write a method to run our training loop, which is basically our optimization loop. And that will hopefully give us some interesting generated images. Now, in order to generate a stylized image, we need to follow the following steps. First, we need to initialize the content image, the style image, and also an initial variable for the generated image. Then we need to instantiate an optimizer. In this case, we are going to use the Atom optimizer. Then we need to run the training loop for a given number of iterations. In this case, we are going to use 20 iterations. Then for each iteration, we are going to do 4 things. First, we will compute the total cost for each iteration. Then we are going to calculate the gradients of the cost with respect to the generated image using gradient tape and automatic differentiation. Third, we will update the gradients. And fourth, we will save the lowest cost and the generated image associated with the lowest cost. And that will be our final image, ultimately the result with the lowest cost, because sometimes the cost may start to increase after hitting a local minima. So we want to ensure that we save the image with the lowest cost during all the iterations in a separate variable, and we will look at that later. Now, this may seem like a lot of steps, but we have already defined all the functions that are required, so it won't actually take a long time. Let's scroll down and go to this section where it says training loop. And let me just import time first, because it'll help us keep track of how long the loop is taking. And also, we will have an array called generated images. And I'm going to use this to store some intermediate results. Okay, let's define our training loop. And we will need to pass on content path, the path for the style image, so style path, number of iterations. Set the default to 20. In our example, 20 will be fine. We also set something called alpha and something called beta. Set these to 10 and 20 respectively. And note that I'm using float values. Okay, so what is alpha and what is beta? So these are our weights that we are going to use to compute our total cost. We multiply the content cost by alpha, and then we multiply the style cost by beta, and then we add the two together. So by using alpha and beta, we can essentially give weights to different costs, and that can help you tweak the results. And let's say you want more of the content features to be prominent or discernible, or you want more of the stylistic elements to be there. So you can tweak these parameters and get slightly different kind of results. Okay, now within this function, we are going to first load the content and the style image. Content is going to be load and process image. This is called, let's not hard code it. This will be passed on in the method. So content path. And similarly, style image is going to be load and process image, style path. Awesome. Now we also need a generated image, which we are going to update. So how do we start? It could be a random image, right? It could be just random values, but we'll get results much quicker if we just use the content image. The generated image is going to be a TensorFlow variable. And in this case, we will have to use contrib.eager dot capital V variable. And the reason we are using .contrib.eager variable rather than simply TensorFlow variable is because we are going to use eager execution mode. Now, in a future version of TensorFlow, it's possible, and in fact, it's likely that this will be removed and you will be able to use a regular TensorFlow variable. But as of now, this is the case. Okay, and the values will be derived from the content image. and data type is tf.float32. Awesome. We have our content image, style image, and generated image, and now we just need to run some optimization algorithm to update this generated image. So this optimizer is going to be the Adam optimizer, and I'm going to set a fairly high learning rate. Again, I've tried this, so I know it will work. And let's also define a best cost. I'm going to set it to something really high and a float, so this will be a high value, and best image to none. And as our loop runs, we will store the best cost and the best image corresponding to that cost in these two variables. Okay, so let's run our loop now, and let's also start our timer. So let's say start time is time.time. Okay, in range iterations. Okay, so with the gradient tape, this is where automatic differentiation comes into play. With the gradient tape context, we will calculate the content cost, and the content cost will be calculated with the content image, of course, and the generated image. Now, we will also need the style cost with the style image and the generated image. Great. And here we will have to add these two to get our total cost. So J total is going to be alpha multiplied by the content cost plus beta multiplied by the style cost. Great. Now we can calculate our gradients by using this tape. Call them grads equal to tape dot gradient, and we are calculating the gradient on the total cost. So total comma with respect to the generated image, right? And then we of course need to use the optimizer and apply these gradients and update the value for the generated image. Actually, this is called OPT, not optimizer. So okay, optimizer, apply gradients, and we need to pass on our gradients and the generated image. In the first iteration, it's just the content image, but as it gets updated, you will see more and more interesting results. All right, let's scroll down a little bit. Now that we have done the updation of the generated image, let's see if the total cost is less than the best cost. Because if it is, then the total cost should be the best cost. And the best image should be the current generated image, because at the moment this is the best image that we have. And because it's a tensor, we are going to look at the just the numpy value or the array. Awesome. Now we can also print out the cost for each iteration. So it's a print cost at some iteration is going to be this. And let's also see how much time has elapsed. Format. So the first variable we need here is first value we need here is the I iteration, then total cost time.time minus start time. Current time when we are printing this minus the start time, this which is before the loop, if you guys remember. Okay, and also the generated images dot append generated image and just the numpy value, not the entire tensor. So in the generated images array, we are going to basically store all the intermediate values for the generated image. Okay, great. So now we are going to basically just execute this and actually return the best image. Okay, so let's run this code cell now, and everything works. Yes, so far. Now I don't know what's going to happen when you call it. If we have not made any mistake, then everything should be fine, but I have a tendency to make spelling mistakes, so we'll see. Our best image is going to be when we call this training loop content.jpg style.jpg, and the best image should be returned to this best image variable, and then we'll look at this later when we plot the result. Okay, so let's execute this. Let's shift enter and let's see what happens. Now, it will take some time for the training to run, so you can actually pause the video at this time, and cost for every iteration will be printed out along with the total time elapsed till that particular iteration. For me, it took me just over 10 minutes when I ran this on this same virtual machine. So you might have to wait for about 10 or 11 minutes or something like that. And when the loop has run for these 20 iterations, you can join me in the next chapter. Till that time, you can pause the video. Hang on a second, iteration is not defined. Okay. Oh yeah, because I misspelled it as I expected. I always do this. There's always some spelling mistake. Iterations. Okay, anything else? I don't know, it looks fine. Let's run this again. And we will find out if I made any other mistake. Let's see. So it seems to be okay, and now everything should be fine. But remember, it's going to take about 10 or 11 minutes for you to go through the whole training process and see all the 20 iterations, okay? And so just pause this video and join me in the next chapter when the training is done. Welcome back. So now that the training loop is complete, you should see something like this. And you can see the cost is decreasing, and the time elapsed, it was almost 10 minutes, so not actually that bad. All right, so now that the training is complete, we will take a look at the best image that was returned. So let's scroll down, and we will use the display image method. So let's go to this blank cell and display the best image. Shift enter, and let's see what we have. All right, so this actually looks pretty good, I think, especially considering that we ran our loop only for 20 iterations. Now, if you want, you can also take a look at intermediate images. But see how in the final image that we have, it does kind of look like a painting. And it has picked up some stylistic elements, as you can see, like those wavy kind of brush strokes from the style image. So this is pretty cool. Now, let's also take a look at the intermediate images and see how the process actually played out as we went through different iterations. Let's see what really happened through those iterations and how the image actually changed. So in the next cell, we will let's write plt dot figure and set the figure size plt dot figure, and let's set the figure size 10 by 10, and then let's run a loop for I in range 20 generated images from 20 iterations. plt dot subplot, say we have 20 images, so we can distribute them like 5 rows and 4 columns, and use our display image method. So display image generated images in the ith generated image for each iteration. Right, and all we have to do now is when we get out of the loop, we will write plt.show. And that's pretty much it. Now we shift enter and execute this code cell. Also scroll down a little more. Alright, so as we go through our training process, our generated image, which starts off being exactly similar to the content image, it changes in this fashion, as you can see. Right, so it changes from looking a lot like the content image to being more and more stylistic, have those stylistic characteristics from the art, the style image. And by the end of it, as we can see, it's pretty stylized. So if you run this loop for about 100 times, I guess you will start to get more interesting results. I'm not sure if they'd necessarily be better